Hello, everyone. Welcome back to this first course in abstract algebra. Today, we're going to be talking about the integers. This is sort of like the prototype of an algebraic structure that we want to replicate and abstract the axioms of this structure and find others out there. So let's try to do that. So today, what I'm going to start with is with the very definition of the integers through its axioms. So the integers, which we write this blackboard Z, like in my hat, you see it. It's a set with the following properties. Now, there are several axiomatic definitions of the integers. So this is one such axiomatic definition. You can find others like the Peano axioms. These are close to the Peano axioms, but you can find other axioms that define the integers. These are the ones that I usually go by. So here is the integers. So first of all, there are two operations. In a previous video, we've talked of the addition, the integers and the addition, but of course, the integers have two operations, addition and multiplication, and Z is closed under those operations. And what that means is that for all integers A and B, we have that A plus B and A times B are also integers. In other words, you can also write that plus and times are what we call a binary operation. So they are operations that go from Z cross Z to Z. Okay, so we have two binary operations. What are the properties of these operations? The properties are that, well, for all A, B, C, A, B, C, in the integers, we have 2A, the plus and times are commutative operations. So we have that A plus B is equal to B plus A. We also have 2B. We also have that plus and times are associative. So A plus B plus C is the same as A plus B first plus C, and the same for multiplication. A times B times C. And another axiom that relates addition and multiplication, which is the fact that there is the distributive laws. So plus and times are distributive, which means that A times B plus C is the same as A times B plus A times C, or that A plus B times C is the same as A times C plus B times C. Okay, so these are the properties of the operations. Of course, we have more axioms. We have existence axioms. I'm going to do that in the next page. So the existence axioms are the following. First, so these are existence axioms. First of all, there is an element, a neutral element for addition. So such that A plus 0 is the same as 0 plus A equal to A. So for all A in the integers, the following happens. There is a 0 element under addition. 3B, we also talked about this last time. There are additive inverses. So for every integer A, there is another integer that I call minus A, such that A plus minus A is equal to minus A plus A is 0, the neutral element that we define in 3A. And 3C, there is an element 1 such that a times 1 is equal to a is the same as 1 times a for every integer a. So these are the existence axioms. And now that we have seen these existence axioms together with uh, the, the fact that there are two operations, the fact that the operations satisfy these properties, and that we have existence axioms, let's stop there and see if this defines the integers. And it turns out it does not, because there are many other objects that satisfy these three properties, these three, 1, 2, and 3. For example, well, the rational numbers and their addition and multiplication, they have two operations. The operations are commutative, associative, distributive, and we have a 0, we have inverses, additive inverses, and we have a 1 in Q. So this is no different from the integers in this respect. If you do the reals under addition or the complex numbers under addition and multiplication, they all satisfy 1 through 3, just like the integers under addition and multiplication also satisfy 1 through 3. So these axioms alone do not define just the integers, they define some structure, which we're going to call a commutative ring with identity. But are there other things that satisfy these properties? There are many such things. For example, I can think of continuous functions under addition and multiplication. Here, these are all functions from the reals to the reals that are continuous. And does this satisfy 1 through 3? Yes, and but now the fact that addition, so what is addition here? If I have two functions that are continuous, the addition of the two functions will be a new function such that to evaluate it, I add the values of f and the value of g, and the multiplication will be multiplication is just the multiplication of the values. In this way, this is also something that satisfies 1 through 3, but now notice that even this property, the fact that these functions are closed under addition and multiplication, is a theorem of calculus. The fact that the sum of two continuous functions is continuous, that's a theorem in calculus, and the fact that the product of the two, the product of two continuous functions is continuous, that is also a theorem in calculus. Now, what is the 0 element in here? The 0 element will be a function from the reals to the reals that sends everything to 0, and our 1 is a function that sends everything to 1. And with that 0 and that 1, now the continuous functions and their addition and multiplication are also something that they satisfy 1 through 3. Are there things that do not satisfy 1 through 3? Well, now we're going to look at, well, the continuous functions again. But let's change the multiplication, and instead of multiplication, let's do composition. So it turns out that the composition of two continuous functions is continuous, so this satisfies 1, but does it satisfy 2? And 2 is not satisfied because the composition is not commutative. So 2 commutativity, for example, fails because, well, sine of e to the x is not the same as e to the sine of x, for instance. So it is not a commutative ring in that sense. And there are other problems with the, well, for example, there are other problems, okay, with this thing. So it does not satisfy 1 through 3. But in any case, there are many things that satisfy 1 through 3. So these two 1, 2, 3 do not define the integers by themselves. So to define the integers, we need a fourth set of axioms that really characterize the integers. Now, before I go into that, let me draw what we usually have sort of a cartoon picture of the integers, which is not good enough to do math with, but the integers, we usually have this cartoon picture of them. Or in a number line, we have this picture that the integers look like this. And we, the high school and elementary mathematics, we actually take this as the definition of the integers, and we are fine with it, and we do math with it, but we need axioms that are going to capture exactly this. And the nature of this is that, well, we have what I call the natural numbers. The natural number for me will be 1, 2, 3, etc. Then there is 0, and then there is the negative numbers. And that is it. So we want to capture that in the integers, there is the natural numbers, there is 0, and then there are the negatives of the natural numbers, and nothing else. So how do we do that? Through what we call the natural number axioms. So there is a subset of the integers, which I call the natural numbers, such that first, the natural numbers is not empty. Second, the natural numbers is closed under addition and multiplication. So if I start with 1, I can add 1 plus 1 plus 1 plus 1, and that will give me more natural numbers, or I can multiply the natural numbers together and get more natural numbers. Now, that concept that there are the natural numbers, 0 or negative numbers, that's what we call trichotomy. Trichotomy says that for every integer, one is exactly one is true. Either a is a natural number, a is 0, or minus a is a natural number. And exactly one of those three is true. That's trichotomy. And the last one, we actually need one more, which is to distinguish the integers from the rational numbers. The problem with the rational numbers is that, well, they are countable just like the integers, but there are infinitely many rational numbers just between 0 and 1. So even though I can number them, they are sort of like packed together. So what we actually are going to call the well-ordering principle says that, let me just write it in the next page so it's not crowded in there. The 4D is the well-ordering principle. It says that every non-empty subset of the natural numbers has at least element. What does least mean in this context with respect to the ordering, which is defined by A is bigger than B if A plus minus B is a natural number. So what we usually say that A minus B is bigger than 0, so that is the ordering we use. Okay, so the well-ordering principle now tells me that the integers cannot be the rational numbers, because in the rational numbers we have things like between 0 and 1, so in the interval, open interval 0 and 1, there is no least element, and that is sort of like proxy for saying that the integers are not dense they're not dense in the number line. Okay, so this cannot happen. That cannot happen thanks to the well-ordering principle. Okay, so now that we have So the integers then are defined through a set of axioms 1 through 4. And then what we're going to do is we are going to prove consequences of the axioms, so theorems about the integers that we use all the time and that follow from these set of basic axioms. So for example, something that is extremely useful is induction. The principle of mathematical induction is a theorem that we prove out of the axioms so that we can prove other things using induction. But the theorem itself, the mathematical induction, is a theorem that follows from the axioms. So let me state it. So let Sn be a mathematical or a logical statement, so something that can be true or false about each one of those statements is about the integers n. So Sn is a statement about the integer n such that two things are true, which is usually the things that we check when we are proving things by induction. Our base case, so S of an integer is true. So there is a base case where the statement is true for some integer n0. And B, every time S of k is true, so every time the statement is true for ak, then it is true for the next one. And that has to be true for all k bigger or equal to n0. So there are two things happening. We are assuming that it is true for a number, for a given number. So for n equals 1 is true, say. And then we are also going to assume that every time we know it for 1k, we will know it for the next number, which is k plus 1. Then the theorem says that S of n is true for all n bigger or equal to n0. As I said, this is usually called, when we are using induction, what we are doing is verifying the hypothesis of this theorem. And the part A is verifying the base case, that there is a first number where it is true. And this is usually called the induction step. And when we assume the kth case, and we then have to prove the k plus 1 case, the kth case is what we call the induction hypothesis. Okay. So as I said in the preliminaries for this course, for the course logistics, I am not going to teach how to do proofs, and I hope people know how to use induction in general. If you are following the same book I'm following, Judson's Abstract Algebra, in the first chapter, there are some basics. And in the second chapter, there are some, he also proves the principle of mathematical induction and uses induction in some examples. So you can find examples of induction in places. But what I want to do here is to actually prove induction using the axioms. By the way, there is some other statement for mathematical induction, which is, and it has a very similar proof, I'm not going to do it here, which is a strong induction. It has the same starting hypothesis, so Sn is a statement, and then there is a base case, and the difference is in B, in that we assume that every statement up to the kth statement is true. So n plus 0 up to the kth statement is true. Every time it's true from the n0 up to k, then it is also true for the k plus 1 case. Then S of n is true for all n bigger or equal to n0. That's a strong induction, and that is also a consequence of the axioms. Here I'm just going to prove the simple induction as follows. So what I would like is for the following set to actually be, that's an F for false statements. So I want to see what are all the counterexamples to my statement. So all the numbers that are big or equal to the base case where the statement is actually false. Okay. If F is empty, then I'm done. So what I want to is assume for a contradiction that there are some counterexamples. So the statement is actually false in some cases. If it is true for every n bigger or equal to n0, then that is what I want to conclude. So for a contradiction, assume that F is actually not empty. So there are numbers in there. Then, well, I want to use what is going to happen. Let me actually draw again some sort of cartoon of what's going to happen. Here is 0. Here is n0, where I know it is true. And then there's going to be integers up to, what I'm going to do is, well, F is going to be a set of integers. There's going to be a least element by the well ordering principle. And that least element where there is going to be a contradiction, where it is false, where the statement is false, is going to be M. But then what I'm going to do is like, okay, if it is false then, and that is the minimum such statement where such a number where the statement is false, the previous one has to be true. So look at m minus 1, it has to be true there, but the hypothesis of induction tells me that every time I find a number where it is true, it is also true for the next one. So it would say that it is also true for the next one, and that is going to be my contradiction, that it is false and true at the same time. Okay, so that is the idea. So, but to start it all, I need to actually use the well-ordering principle, and if we go back to the well-ordering principle, here it is. The well-ordering principle was for every non-empty subset of the natural numbers has a least element. But now, right now, if n0 in n sub 0 is 0, this is not a set of the natural numbers. It might be a set of the non-negative integers. So then we have that this set of counterexamples is either in the non-negative integers, or it is strictly speaking contained in natural numbers, and then I would be able to use the well-ordering principle. But if it is the case that n0 is actually 0, then part A, the base case part, tells me that S of 0 is true. But if S of 0 is true, then 0 cannot be part of the counterexamples. So 0 is not in the counterexamples, and therefore F is always actually contained in the natural numbers. And since now I have that F is contained in the natural numbers, I can actually use the well-ordering principle. By the well-ordering principle, there is a least element, because you see it is contained in the natural numbers, and it is not empty, so there is a least element. Let's call it M. Okay. And well, it is in the counterexample, so so we know that the statement is false. Is false for M. Then also notice that M is strictly bigger than N0, so m minus 1 is bigger or equal to n0, and it is less than the minimum, so the statement at m minus 1 must be true, because m minus 1 would not be part of the counterexamples. But now that we know that it is true for m minus 1, then part B of the assumptions, our assumption in part B says that every time it is true for a k, it is true for the next one, as long as k is bigger or equal to the base case. And we do have that m minus 1 is bigger than the bigger or equal to the base case. That is true, and therefore we this implies that s of m minus 1 plus 1 is true, but this is s of m, and therefore s of m is true and false at the same time. So that is a contradiction. We have reached a contradiction and the contradiction was with what? It was with the fact that we assume that f was non-empty, so thus f must be empty, and so there are no counterexamples, so s of n is true for all n bigger or equal to n0, which is what I wanted to prove. So this is a proof of induction using the axioms, in particular using the well-ordering principle. If you go to Judson, actually, it turns out that that the well-ordering principle is actually equivalent to induction. I just proved that the well-ordering principle proves induction, but you can actually assume induction instead of the well-ordering principle as your axiom and prove the well-ordering principle. So it actually goes both ways. So now, what are more consequences? I'm not going to prove these, but they are actually proved in Judson's book. So I suggest you read it there. So for example, one can prove the binomial theorem. Using, now that we know induction, one can use induction to prove the binomial theorem. So, for example, for integers, the binomial theorem says that if n is bigger or equal to 1, then the power, the nth power of a plus b is the sum from k0 to infinity. I did the same exact mistake when I taught this just a couple days ago. The sum from 0 to n of n over k, and choose k, a to the k, b to the n minus k, where n choose k is the combinatorial number which can be computed as n factorial, k factorial, n minus k factorial. Okay, so for example, one can prove the binomial theorem just using the axioms and using induction. What other things are usually proved in fact, usually proved in a number theory class? So if you go actually to my one of the books that I've written, which is actually free, available for free in my website, Number Theory and Geometry. So if you download Number Theory and Geometry, you can find the axioms that I just used and proofs of a number of theorems, such as the ones I'm going to state here. So something we use also all the time is what we call the division algorithm. The division algorithm, or long division. It says that let a and b be integers with b bigger than 0. Then there are unique Q and R in Z integers such that A is B times Q plus R. Those would not be unique unless we put the remainder in some bounds. So if you fix the remainder between 0 and B, then there is a unique Q and R with that property. And this is just a very important theorem that we use all the time when we do proofs about divisibility, for example, in the integers. But the interesting part is that such a theorem can be also proved in other types of rings that share some of the axioms that the integers share. So if you go through the proof of the division algorithm, you can try to keep track of what axioms you're using and then prove this, for example, for polynomials over the polynomials with coefficients in the integers. There are some, there's a theorem like this with B, like a harmonic polynomial, then you can do the division algorithm like this one. Other theorems that are usually proved in the number theory class, I'm not doing here, but again, it's in Judson, is theorems about prime numbers. So let me define what a prime number is. An integer p bigger or equal to 2, 1 is not a prime number, is a prime if its only positive divisors are 1 and p. Okay, so we know the prime numbers are 2 and 3 and 5 and 7 and 11 and 13 and 17 and 19 and etc. Okay, so what about prime numbers? Other theorem that one can prove is one of the most important theorems in number theory that Euclid proved like 2,300 years ago or more, that are infinitely many prime numbers. Or what we call the fundamental theorem of arithmetic, which says that every integer n bigger than 1 has a unique prime factorization. So there is a prime factorization, and it is unique when we write it like this, as p1 to the e1, p2 to the e2 times pr to the er for distinct primes, p1 less than p2, so we write them also in increasing order, and exponents ei bigger or equal to 1. So those are very important consequences of the axioms of the integers that I'm going to use to prove other things later on. And I think I'll stop here. This is as much as I want to say about the integers themselves. And in the next video, we're going to use the integers to construct new algebraic objects, which are the rings of integers modulo n.